Hello everyone, nice to talk to you all. So this class we're going to continue our topics on the fundamentals of environmental engineering and science. And specifically we're going to learn about filtration and disinfection. So before we start the new contents, let's do a quick recap again. So last class we derived some equations regarding the hardness of water. So basically we want to know how to calculate the total hardness of water. Further, we differentiated the carbonate hardness and non-carbonate hardness by using the bar graph there. And also we learned about how we can soften the water with lime and soda method. So this class we're going to learn about more methods to further treat the water quality that are potentially can be installed downstream of the processes such as the softening process or the coagulation, flocculation, clarification process. All right. So the first one we're going to learn briefly is about the sedimentation. So sedimentation means to remove the solid particles in the water by their gravity. So for example, let's say that we are processing the water through a channel here. And then because of the particle gravity, so larger particles, they will just settle down by vertically, right? But at the same time, the flow is going in this direction. So what's going to happen is that the particles would follow a trajectory that looks like this. So the horizontal velocity is caused by the overall velocity of the flow. And we can calculate, actually this horizontal velocity can be calculated by Q, which is the flow rate, divided by the cross-section area of this duct, right? And then this vertical velocity, Vy here, is called the settling velocity. Okay, so first, if we consider, so there are different mechanisms for removing particles by sedimentation, and the most simple one is actually the free settling of discrete particles, which means that the particles, we can see them as spherical, right? They're just a single particle, because this is most likely not the case if we think about the components in the water, right? So the particles in the water are very unlikely to be spherical. And at the same time, the flocculation process will create a lot of particles that are forming these kind of aggregates, right? They will not have a regular structure, regular shape. So basically this free settling of the discrete particle is the most simple mechanism of the particle settling. Okay, but on the other hand, we can use mathematical methods to predict when these particles will settle. So for the settling of these discrete particles, only the particles that have the settling velocity greater than a specific value can be removed. All right. So basically, if the particles will have a slower velocity for settling, they will just flow with water, right? So there's always a critical size of the particle that can settle down and then within this channel here. The reason why I say that there is a critical size is because let's say that if a particle has exactly the shape or the size of a water molecule, then there's no way that this water molecule will settle down, right? So basically, there will exist a critical size that the particles with a size that's larger than this critical size will settle down, while the particles with a smaller size will not settle down or will not get collected by sedimentation. All right. So to find out what this velocity is, actually, we need to further analyze the parameters in this sedimentation process. So we can define a time which is called the hydraulic retention time. That's just calculated by dividing the volume of the sedimentation basin. So typically these sedimentation basin will look like a rectangular shape, right? It looks like a pool in there while the water is flowing this way, and then after that they're going to flow to the next module there. So the retention time is just calculated by the volume of this basin divided by the flow rate of the water. Okay, so further we can calculate the settling velocity. So as according to the Stokes-Einstein equation, the settling velocity can be calculated by rho particle minus rho water. So basically the density of particle minus the density of water multiplied by the particle size multiplied by the gravity divided by 18 mu. So basically the mu here is the viscosity of the water. Okay, so you can see that basically, so here these are the density of the particle and the density of water. dP is the size of the particle and g is constant. It's just the gravity acceleration, right? And the viscosity of water is also a constant. So you can see that actually the settling velocity is proportional to the particle size squared, right? So basically it means that the larger the particle, the faster it can settle down, okay? So this is about the particles. Then how do we decide whether the particle will settle down or not within this sedimentation basin? So this critical velocity we're talking about is the overflow rate, okay? Although it's called a kind of like a rate, but actually it has the unit of meter per second, which is the which we call them as the overflow rate, okay? So here is a more specific way, or more straightforward way to look at how the particles are being removed in the sedimentation basin. So for example, if we have a water flow going in this way, and then we know that the smallest particle that can get removed from this basin actually will follow a trajectory that's starting from the top left to the bottom right, right? So if the particles will have a has a smaller settling velocity, then they will go through this trajectory, and what that means is that the particles will actually get escaped from this sedimentation basin. Well, if the particles have larger settling velocity, then that means that they can go from this trajectory and then get collected, all right? So how do we calculate this critical velocity then? So according to the geometry of the sedimentation basin, actually this can be calculated by just the height of this basin, which is h, divided by the retention time, right? So this is going to be the critical vertical velocity that's deciding whether the particle will or will not be able to settle down in the basin. So then we can further plug in this time here. So the time is equal to v divided by q, right? And further, this v is equal to what? H multiplied by W multiplied by L. Well, the W is the width. So basically this basin will look like this, a cubic shape, right? And L is the length, right? So if we further plug in these parameters, so the Q will get to the denominator, and then we can cancel out the H, right? So we're going to have Q divided by O multiplied by W. And further, if we look at the L and W, actually this product is the surface area of this sedimentation basin, right? So it's just the area that's, if you look from this direction here. Okay? So basically, if we calculate this overflow rate or this critical velocity, then we can compare against the settling velocity of the particles and then decide whether they will get removed or they will not get removed. And typically when we design a sedimentation basin, we will specify the overflow rate so that we can make sure that the particles with a higher settling velocity will get removed in this sedimentation basin. All right? So the overflow rate is the most important parameter when we design these sedimentation processes. So here we have a very simple example here, and also this is one of your homework problems. So let's say that we have a certain water treatment plant that uses a velocity or use a flow rate of 1 meter cubed per second, and then it has 10 sedimentation basins. So what that means is that, let's say this is the main flow of the water, and then it will separate into 10 of the sedimentation basins, right? And then what that also means that for each of the sedimentation basin, it's gonna just use 0.1 meter cubed per second of the flow rate, okay? And then it further specifies a overflow rate, okay? So as you can see, this overflow rate should have a velocity a unit of for velocity, right? So it's going to be meter per second. Okay, so here instead it shows the unit in this way. So it's actually a easier way if we look at the definition for the overflow rate. That is the flow rate divided by the surface area, right? And then we can actually convert this into meter per second by just plugging in, and 1 day is equal to 24 hours multiplied by 3600 seconds, right? So basically what we can do is that we can calculate, we can build up this equation, overflow rate equal to Q divided by the area, right? So we know that the overflow rate is equal to 15 meter cube per day per meter. And then we know that the Q is equal to 0.1 meter per second. And here we have also have the area here, right? So we can further calculate what is the surface area of this tank, okay? So what this simply means is that if we construct a sedimentation basin or turn up the sedimentation basin here, then the particles with a terminal velocity that's higher than this overflow rate will get settled down, will get collected, while the particles with a terminal velocity that's smaller than this overflow rate, they will just get escaped from the sedimentation basin, and we can further collect them using the filtration method. Okay, so also you may wonder, then since we have this overflow rate, then how does this relate to the particle size? So we can actually use or directly plug in this overflow rate to the settling velocity. So basically this tells us that if we can solve a particle size that's coming from this equation here, then the particles with a larger size, then they are going to get collected, while the particles with a smaller size, for the particles with a smaller size, they can just get escaped from the sedimentation basin. All right, so this is the general idea of the sedimentation, and as we have introduced, this is the first or the most simple mechanism for removing particles by sedimentation. And there can also be a flocculent settling. So what this means is that, as we have introduced before, the coagulation, flocculation, and clarification will generate larger particles, right? So what this means is that the particles will grow into larger flocks as they descend to the bottom of the basin, right? So what this means is that they're going to settle faster as particle size grows faster. So we also have the mechanism that's called the zone or hindered settling or compression settling. So basically what this means is that we have a zone that have very highly concentrated flocks, and this will create a lower settling velocity because some water are trapped in these flocks. Okay, so this is a general idea for the sedimentation. And as we have introduced, for particles with smaller sizes, they can escape from this sedimentation process. And what we can do is that we can further use filtration to remove these small unsettleable solids, right? And in terms of the filtration, it is actually mandatory for surface water and shallow groundwater because there are a lot of colloids. And although we can remove these colloids by coagulation, flocculation, clarification, there might still be some suspended particles in the water. So we have to completely remove them using the filtration method. And the filtration has the highest efficiency in terms of removal of the particles. So as it has been shown in this graph here, so what that simply means is that filtration will typically use these filtration medium here. It can be composed of sand, or it can be a multi-medium. For example, you can also have the support gravel or use some other components in the filtration components here. And then the particles or the suspended particles will just get trapped in these filters, and then basically the filtered water can further get collected and go to the downstream processes. Okay. So here is a brief introduction about the filtration principles. So actually the particles can get collected or get filtered by different mechanisms. For example, it can be straining. So what straining specifically means is that we have a lot of larger particles. So if the particle size is comparable to the size of the sand gravel or the sand particle, then they're too large to pass through the sand medium, right? And there can also be interception. So interception means that there are smaller particles, but they basically get attached onto the surface of these sand particles. So what that means is that while they are being transported in water, right, then the surface of the sand particle and the surface of these larger particle will interact each other, and then the particle will get attached onto the medium. So there can also be flocculation, which basically is the same idea of the coagulation flocculation. So basically the particles will get attached onto each other, right? So let's say if we already have some particles on the surface of the sand, and then if we have another particle passing through, then they can get attached. And there can also be sedimentation, which simply means that the particles are too large, so they just by gravity they'll get collected onto the sand particles. Okay. So in terms of the process, the detailed processes of the filtration. So what happens is that let's say if we have a very clean set of sand filters, then what happens in the beginning is that the particles will just get retained on the top layers of the media. So for example, we have this block of sand here, and then the untreated water will just go by gravity, right? Go from the top to the bottom. Then initially these larger particles, or these particles in the water, will just get attached onto the surface, right? Then after a while, as you can imagine, there will be more particles get collected on the sand filter, and then what this also means is that it's going to create a smaller cross-section area for the water to pass through. So for example, we can think of it as this way. So let's say these are the sand particles in the basin, okay? And then as the particles get collected onto the surface or onto the sand filter, then the water can only go through these smaller gaps in the water, in the filter here. So this smaller gap will create a larger velocity. Okay, the water velocity will increase. If the water velocity increases, then they can break these particles apart into smaller particles. And if we have smaller particles, they can further get penetrated deeper into the sand filter, right? And basically they will force these particles to move down to deeper layers of the medium. But when the particles will penetrate the media, then that simply means that the filter is not working at all, right? So the effluent turbidity will increase simply because we have too much particles getting escaped from this filter here. So the method we can use to treat the filter is by backwashing, okay? So we can use some cleaner water to backwash the filter, and then we can remove these larger particles, and then send these backwashed water and collect them for further treatment, right? So in this way, we can regenerate the filter from this process. And because of that, as you can think, let's say we're a manager of a water treatment facility. So can we just build one filter for the purpose of filtration? No, right? Because the water treatment is always a continuous process. So if we realize that the filter is contaminated or there are particles getting escaped from the filter, then we need to use the backwashing to clean these filters. But by cleaning these filters here, we have to stop the upstream flow here, right? And then to push the contaminated water to the basically back of the filter there. So for these filter setups, we always will construct multiples of them so that when we can easily take them offline when we're trying to clean up these filters, okay? And in terms of the design for the filters, there's one important parameter. So similar to the sedimentation process, we have a parameter that's called loading rate. So again, you can see that this is a rate, although it's called a rate, but basically has the unit of velocity, which is meter per second. Okay, so the loading rate is calculated by dividing the flow rate of the water by the surface area, or by the surface area of the sand filters. Okay, so or it can be different types of filters, as we can introduce later on. Okay, so one thing we need to make sure is that the loading rate is always below the maximum loading rates. So for each type of filters, there's a maximum loading rate, or there's a maximum velocity of water that can flow through the filters. So again, for this filter here, all right, there's sand in the filter here, right? So if the velocity is too high, let's say the VA, or the loading rate is too high, if the VA is larger than the VA prime, which is the maximum loading rate, then that's going to create a strong pressure drop through this filter, right? It's very easy to damage the filter during this process. So we always need to make sure that for our design filtration system, we need to make sure that the loading rate is smaller than the maximum loading rates. Okay. So what are the maximum loading rates? It really depends on which type of filter we're talking about. So the most simple type of filter is called a single media rapid sand filter. Okay, so this basically this filter is just composed of sand. Okay, so we can have some support gravels, but typically these support gravel will have a larger size in terms of the material here. So basically this gravel doesn't really filter anything out from the water. So it's just the sand that's used as a filter in this single media rapid sand filter. So as we have introduced earlier, typically when we construct the filtration system, we need to build multiples of them. So that's why for these single media rapid filter, we'll build at least 4 units. Okay, and the size of each unit can take up a surface area of at least or up to 100 meter per second, 100 square meters. And in terms of the backwashing process, what we'll do is that we can pump the water back through the media, and then also because we're flushing the water back in, the sand bed will expand, okay, and then the particles will get removed. And typically this backwash water will consume 2 to 4% of the treated water. So you can see that this is considerable amount of water we're using to regenerate this filter. And in terms of the maximum loading rate, it has to be smaller than the 235 meter cube per day per square meter. Okay, so when we design the rapid sand filters, we need to make sure that the loading rate we calculated is smaller than this value. So there can also be the multimedia filter. So as you can see, if we use sand here, then we know that the sand particle size is quite comparable to each other, right? So what this means is that no matter how large the particle in the water is, they will deposit quite uniformly in the sand. Okay, so what this will create will cause is that basically this will get the upper layer of the sand to be really packed with particles, because there's no differentiation between the particles in terms of the particle size. No matter whether they are large or they're small, they will all get deposited in this first layer, or the top layer of the sand. So what we can do to solve this problem is that we can create this multimedia filter. So it can include several media, including sand, anthracite, or garnet, right? And then we can basically determine their size, well, with the largest and lightest on the top. So if we have larger particles on the top, and then it can basically remove these larger particles. Well, if we have smaller sand at the bottom, so after these larger particles are removed, then we'll have smaller particles, right? Smaller particles will get deposited or get filtered at the lower layers of the filter system, okay? And in terms of the effluent quality, it is quite similar compared to the sand filter. But as you can see, the advantage for this process is that actually can be more efficient in terms of removing the particles, right? And when we try to regenerate the filter systems, it doesn't create as large as a pressure drop compared to the sand filtration. Basically, it can reduce the resistance and increase the capacity due to the use of the large anthracite media, which is located at the top of the filter. And the loading rate can be up to 300 meter cube per day per square meter. So you can see that the maximum loading rate is a little bit is higher. It's actually higher compared to this single media rapid sand filter, which is because we're using multiple media here, right? And in terms of the backwash, we can use air and water mixture to clean up these particles. And so furthermore, in terms of the design considerations, typically for the water treatment plant, they will try to construct even number of filters. For example, they won't construct, first they won't construct one filter only, because as we have introduced, sometimes we need to backwash the filter, right? So which means that this filter has to be taken offline. And then under this situation, we have to use the backup filters to clean up the water, because we cannot directly cut the water supply just because of the need for cleaning the filters. All right, so we can either use 2 or 4 or 6. Basically, we need to use even number of filters, and this is easier for the this is basically for considering the ease of the construction. And also we need to make sure that the filter loading rate should not be higher than the maximum loading rate. Okay, this is the most important design criteria for these different types of filters. So we can go through maybe one of the example here. So let's say that we're designing a filter, right? Rapid sand filter here, and then it has a flow rate of 0.8 meter cube per second. Okay, and then it basically asks us how many of these rapid sand filter boxes it needs for reaching a loading rate of 110 meter cube per day per square meter. Okay, so as we have introduced earlier, this loading rate, or VA, is equal to Q divided by A, right? So the A is the surface area of the filters. Okay, so what we can do is that we can first calculate what is the A that's required for this loading rate. So A is equal to Q divided by VA, right? One thing we need to make sure is that we need to convert these units all into the standard units, basically to convert this day into seconds, right? And after we calculate this A here, we should divide that by the basically the surface area of each of these sand filter box. Okay, we need to divide that by 100. Okay, so in this way we can calculate what is the number of the rapid sand filter boxes we need. But let's say, for example, the result we get from that is 3.5. Okay, let's say that the number of sand filter boxes we get is 3.5. So how do we decide the final number of the sand box? Because we cannot easily just build half of the filter box, right? So we can either round it up or round it down. Okay, so here we decide to round it up to 4, basically because of 2 considerations, right? So the first one is that by building more capacity of the filter here, then that will lower the loading rate. So that's going to be safer for this operation of the filtration here. And secondly, we need to know that there are always even numbers of the filters we need to construct. Okay, so another example is that let's say the value we got is 4.3. Okay, so how do we decide that? So should we round it up or round it down? We can try to round it up to 5, but again, because of the design consideration, we need to have even number of filters. We can change it to 6, but actually 6 is going to be too large, or because of we also need to consider the expense associated with the filter system here. Okay, of course 6 is okay, but the cost may be high. So here we decide, if we decide to round it down to 4, then we need to make sure that simply because we reduce the number of the required sandbox filters, sand filter box, right? So by reducing that, we need to calculate a new loading rate. So what we need to do is that we need to calculate this VA equal to 4 multiplied by 10 multiplied by 10. So 4 is the number of sand filter boxes. 10 multiplied by 10 is the surface area of the filter. Okay. So what we need to make sure is that this loading rate is smaller than the maximum loading rate of the filter box. And here you can see that we're using this rapid sand filter box, which means that its maximum loading rate is 235 meter per second, right? Or meter cube per day per meter square. Okay, so we need to make sure that this calculated loading rate is smaller than 235. If it's larger than 235, then it means that it's going to be dangerous to operate with 4 of the filter boxes. So what we need to do is we should use 6 here. But if the loading rate is smaller than 235, then it means that we are okay with 4 here. Okay, so the similar principle will apply if we are trying to design these dual or these multimedia filters, right? So typically we'll know what is the loading rate, and then we also need to know what is the flow rate, and then based on the surface area and also the surface area of each single unit, we can calculate how many filters we need. But we need to make sure that first, the number of filters are even, and secondly, the filter loading rate should be lower than the highest or the maximum loading rate. Okay, so after the filtration, the final or the last important process we need to know is the disinfection. So what disinfection does is it's going to kill the pathogens, and we learned from earlier classes about the definition for pathogens. So the pathogens are basically the microorganisms that can cause waterborne diseases. For example, the microorganism can include bacteria, viruses, protozoa, and helminths. And typically, when we try to measure the number of the pathogens, or we try to define a parameter to evaluate the pathogens, we're going to use the coliform bacteria as an indicator for these organisms. The reason why we use coliform bacteria is because it's very easy to detect, and secondly, their presence indicates that there is pollution by feces. And what that further means that if there is feces, then it means that there are further presences of the pathogens. And of course, there are limitations associated with just using the coliform bacteria as an indicator, because the coliform bacteria will die off quite quickly. So their die-off rate is faster than the viruses and protozoa. So what that means is, without the coliform, it does not necessarily mean that there are no other pathogens. There can be other pathogens, but it's just the coliforms die off too quickly. Okay, so here I show some pictures of these microorganisms in the water, and our goal is actually to remove them from the water. And you can see that they can actually contain very complex structures. Okay, so to completely remove them, we need to use some strong method to kill these pathogens from the water. Okay, so here's a quick question here. So why do we use the coliform bacteria as an indicator for water biological quality? So if you recall from the previous slides, it's actually because first, the coliform bacteria are easy to detect, and also the coliform bacteria indicates that there are physics, and that indicates that there are other pathogens in water. So we should choose C here. Okay. And in terms of the method we can use for disinfection, so the chlorine disinfection is the most widely used method for removing these pathogens. The reason is that the chlorine is a very strong oxidant and it can kill the living things or the living pathogens in the water. So the detailed process is that the chlorine can react with water. So first chlorine will dissolve in the water and then react with water to form the hypochlorous acid, okay, and further it will also generate the hydrochloric acid. And of course the hypochloric acid can further get dissolved or can get dissociated into hydrogen and hypochlorite, and it has a dissociation or the equilibrium constant of 7.54. And in terms of the amount of chlorine we need to put in the water, we need to guarantee that the concentration of the chlorine is around 2 milligrams per liter before it enters the distribution system. And also the concentration of the chlorine in the water in the distribution system, let's say from the tap water, should be larger than 0.2 milligrams per liter. So in this way, it can also disinfect the water within our homes, right? And further, in terms of the water pH for using this chlorine disinfection, we typically will guarantee that pH is below 7.54. So what this means is that we're going to make sure that, or we prefer the acidic water. The reason why we prefer the acidic water is that with more proton ions in the water, then the equilibrium is going to go this way, right? Simply because there are higher concentration on the right hand side. So the goal is that to keep a relatively high concentration of the hypochlorous acid, simply because the hypochlorous acid is more effective compared to the hypochlorite. And further, the chlorine can react with ammonia to form the chloramines, and which is a weaker disinfectant. But if we want to achieve the highest performance of the disinfection, we want to make sure that the concentration of the hypochlorous acid, or the HOCl, is the highest. Okay. Further, if we can measure the concentration or the chlorine residue in the water, it is quite related to how much chlorine we put in the water. So, for example, if we have a cup of water in here, okay, we know that the water itself may contain some organics inside. So if we start to put in chlorine in the water, then first we will not measure any residue there. That is because the chlorine is destructed by the reducing compounds, for example, organics, right? And then the chlorine residue will increase, and this increase is because of the formation of the chloroorganic or chloramine compounds. And these compounds are relatively unstable, and also it can further get oxidized by the chlorine. So as we further increase the chlorine dose, as you can see, the chlorine residue will decrease, and this is because of the destruction of these chloramines or chloroorganic compounds by the oxidation. And after these compounds are fully oxidized, then the residue or the chlorine residue concentration are going to increase. Okay, so this is because of the formation of the chlorine and presence of the chloroorganic compounds that are not destroyed yet. Okay, so this is going to create a concentration that's solely dependent on the chlorine dose here. So in terms of the disinfection, we also want to make sure that basically we want to make sure that the chlorine residue is in this regime, right? We don't want to leave them in here because the chloroorganic or chloramine compounds, they're not very stable here, so they can really easily get dissociated and then convert back into these polluted species in the water. Okay, so one thing we need to pay attention to the chlorine disinfection is the disinfection byproducts. So during the disinfection, the chlorine can react with many other species, and mainly it is the existence of the bromide in the water that's going to cause the formation of these byproducts, and most of the time they're toxic. Okay, so these byproducts might include the THMs or HAAs. So here I won't further introduce what these species are, but we need to closely monitor the concentrations of these byproducts. So in terms of the disinfection, we can also use the chlorine dioxide to remove the or to disinfect or to kill the pathogens. And the advantage for using the chlorine dioxide is that it is a weaker oxidant, and also it will not form these byproducts or oxidation byproducts from the disinfection. But it will also form the chlorate or chloride, which are toxic in the water. We can also use ozonation. So I think that in the earlier video that I showed in the class, the tour of that water treatment plant actually used the ozonation, used the ozone to disinfect, and also use the UV light to disinfect the water quality there. Okay, so the ozonation can actually kill everything instantly, but the problem for ozonation is that the ozone dissolved in water is not very stable. Okay? It just have a half-life 10 to 30 minutes. What that means is that if the water in the treatment plant stays for a time longer than 10 to 30 minutes, then the ozone concentration will decrease to zero. Okay, and that's not going to further disinfect the species in the water if there are contaminants further introduced in the water system. Another disadvantage for ozonation is that it's going to form the bromate, which is toxic again. So you can see that there are a lot of counterbalances we're talking about here, right? On one hand, we want to disinfect the water to remove all of those pathogens, but on the other hand, we don't want to form these toxic byproducts from this disinfection process. And further, in terms of the UV light, it will kill the pathogen and on a specific location, right? So for the UV chamber, it will look like a tube like this, right? And we can shine the UV light here. And then that's going to achieve the disinfection here. But similar to the ozonation, right? Ozone can still dissolve in water, but UV light cannot dissolve in water. It's just radiation here. So it can only kill the pathogens in this specific reactor or location here. So simple problem, why is chlorine commonly used for city water disinfection? So it can be either chlorine is a strong disinfectant, it kills all the pathogens in a few seconds, or the chlorine is stable and can maintain effective for a long period of time, or chlorine does not form disinfection byproducts. We know that chlorine will form these disinfection byproducts here, right? So it's that we're not going to use C here. And from A and B here, actually we'll choose B because the chlorine is not the strongest disinfectant, okay? And also it's not going to kill all of these pathogens in a few seconds. And the disinfection process happens along the entire process during the water distribution. So that's why we require the chlorine concentration in the distribution system to be still higher than 0.2 milligram per liter, right? So the disinfection process for chlorine is a long process. And so you can see in this class we learned about the sedimentation, filtration, and disinfection. So earlier we learned about the coagulation, flocculation, clarification, and also the softening process. So that pretty much covers all the important processes for water treatment. And there are commonly people who use other treatment processes to further clarify or further treat the water properties. For example, we can use the microfiltration or ultrafiltration process. So for this filtration, we're going to use those polymers, and then they can achieve a higher or better performance in terms of removing the particles or the bacteria from the water. So what happens is that the filters are going to look like the cylindrical shape, right? The water are going to be introduced from the side of the or outer region of this cylinder here. While the water is being transported, they will go through these fumes or filters, layers of filters. And then the larger particles will just get deposited onto these filter sheets. And then the cleaner water, or just the water molecule, can get permeated through these filters and then exit from the center of this cylinder here. So here it shows a picture of these filtrations, or biofilm, microfilm filtration, or the microfiltration process. Okay. So we can also use the advanced oxidation processes, basically to use these highly active hydroxyl radicals, which is much stronger oxidant compared to the chlorine in the water. But typically this is because we are going to use these devices when there is a higher standard in terms of regulating the disinfectant in the water, or if we require a very low or a complete removal of the pathogen or organics from the water. Okay, so we can also use the carbon adsorption to remove the taste and the odor of the water, and also can remove some of the dissolved organics in the water or heavy metals, or we can also use that for dechlorination if we introduce too much chlorine in the water. So the adsorption, as I introduced earlier in the class, the adsorption mainly happens at the surface of these particles here. Okay, so these particles will have a very high surface area, and then these molecules, odor molecules or organic molecules, they will get attached onto the surface of these particles here. So there will be a problem if we use this adsorption for a long time. This is mainly because the surface area of these particles or of these carbon, they're just limited. There's no endless surface area for us to conduct the adsorption here. So what's going to happen is that after a long period of operation, then these molecules will just get leaked from the adsorption setup. And we call this process as the breakthrough of the adsorption. So as you can see here, it is showing the adsorption process for removing certain chemicals from the water. And you can see that in the beginning, the concentrations of these chemicals are close to zero, right? This means that adsorption is happening at a very efficient way. But after a longer period of operation, the concentration of these chemicals will increase and even go to the saturated concentration. And this means that the adsorption is not effective under this situation. And you can see that similar to the filtration system, for the adsorption, we probably also need to build several setups, right? So that we can easily take one of the setup offline for regeneration and then put it back online. So we cannot just simply deploy one adsorption system in the water treatment process. So we can also use the aeration. So what that means is that we can generate bubbles or make the water more turbulent. So what this can do is to remove the gas in the water, and also it can help oxidize the iron. So it can oxidize the ferrous ion into ferric ions. And the ferric ions typically will have a lower solubility in water, so that we can remove these ions from the water. Okay? So that's all for the contents of this class. We can just do a quick review here. So in this class, we want to know what are the major differences between the single media sand filter and the multimedia filtration systems. And basically want to know how we can design these filtration systems, and why the sand is graded, or why the sand is sized when they're being used in the filter, and how we can clean up the filter. We can use the backwash water to remove these particles, right? What are the pathogens? Why do we use the coliform bacteria as an indicator? Why is chlorine commonly used to disinfect the drinking water? And why it's more efficient when the pH is less than 7.54, which means that water is more acidic. So we introduced the major disinfection byproducts, and we introduced some other methods, for example, membrane process, or the carbon adsorption process, or aeration, to further treat the water quality. Okay, so that's all for the contents of this class. Let me know if you have any questions. Thank you.